Welcome to another fun-filled edition of Comet Algebra. These are the notes for section 9.5, Graphing Reciprocal Functions. If you recall, when we did the poster projects that are hanging in the hallway, one of the groups did have this as a parent equation. They might have had like y equals 3 over x. And then they had to graph it, the original, and then move it up, down, left, right, and so on. So they kind of got a head start on this section when they did that poster project, but stop by and look at them in the hallway if that's helpful. A reciprocal function is simply y equals 1 over x. That's the parent equation. And if you graph that on your calculator, you will see that it's a two-piece graph, and it's called a hyperbola. The branches of the hyperbola get very close to the x and y axis, but they never cross them. And this, we learned earlier, is what is defined to be an asymptote line. Where the two asymptote lines intersect each other is what we call the center of the hyperbola. Now, I'd like you to note that if you entered this on your calc and you're looking at it, your calc does not graph the asymptote lines. It won't tell you that they're there. You simply have to figure it out by looking at the graph and maybe looking at the table and figuring that out. I'd just like to review that when we write the equation of the line that is the asymptotes, just to remind you, because we sometimes forget, this equation, y equals 0, this is the equation for the y-axis. When we write y equals 0, this is a horizontal line. I'm sorry, this is the vertical line. Scratch that. Sorry, my mistake. I owe you a starburst. So once again, x equals 0 is the equation of the y-axis, which x equals 0 are vertical lines. And when we write the equation of the x-axis, this would be the horizontal lines, then we use, that's the form y equals 0. So when we move the graph up and down, we still have to state the equations of these asymptote lines, and just to get it straight, which one is the y equals and which one is the x equals. So reviewing again what we learned about transformations, this, I think it could be called the graphing form of a hyperbola, but I could not find that in your book. So I didn't want to state that for sure. But connecting back to what we learned, when we added a number, this number k would be the value that moves the graph up and down. And this number h, it's, remember that opposite thing? It moves the graph left and right. And this a can be any number. And of course, the f of x could always be replaced with a y. So we always have the x and the y in our equation. In this example, we are asked to do three things. First, to graph the hyperbola, then identify the asymptotes, and also state the domain and range. So enter this into your calculator, and just let me remind you, whenever you're entering functions that involve fractions, your calculator will not know what the numerator and denominator are unless you put them in parentheses. So when it's a trinomial, whatever, binomial, put that denominator in parentheses and then enter this as -1 divided by parentheses x plus 2, and then add your plus 3. So if you enter that and graph, you should get a two-piece graph, one piece running approximately like this, and the other about like this. And of course, we notice right away that both, looking horizontally here, both branches of this hyperbola approach this dotted line, and then looking vertically, both branches approach this dotted line. And we need to identify those asymptotes. And you can look at the table in your calculator, and if you suspect that something is happening right here at +3, and if you look there where you will see that as x gets bigger and bigger, it gets closer and closer to 3, 2.8, 2.9, and so on. And then if we suspect something is going on here where x is -2, if you look on the table where it says x is -2, you will have an error message. So we kind of just by inspection found that we have a vertical asymptote at x equals -2. I'm going to abbreviate that VA. And we have a horizontal asymptote at y equals 3. And there's some hints to this in this equation. Since we moved it up 3, the center of the hyperbola went from the origin up 3 spaces, so that makes sense. And we moved it to the left 2 places, and that makes sense for the vertical asymptote. Then to state the domain and range, these aren't too difficult, because the domain is everything except where the graph doesn't exist. So if your eyeball is looking left to right here, this branch goes on forever in the negative direction, this branch goes on forever in the positive direction. The only place the domain doesn't exist is at -2. So we say that the domain is all x except, draw the bar that means such that, except x is not equal to -2. And likewise for the range, your eye is looking up and down at this graph. The branches go up and down forever. The only place that the y is not defined, y is not equal to 3. All right, another term to be familiar with is points of discontinuity. Discontinuity, I tried to say this 3 different ways. It's where x does not exist. It is a hole in the domain. It is where you actually have to pick your pencil up to finish drawing the graph. When we were doing the algebra sections of this chapter, we called these excluded values. This was one of the reasons we spent so much time on these, is because of what happens when we graph. So excluded values are where the graph does not exist. There are 2 types that we're going to talk about: asymptote lines, and we will be talking about both vertical and horizontal asymptotes, and a hole in the graph. Now what this actually looks like, if I could just sketch one of the branches of a hyperbola, the hyperbola will be cruising along right here, and suddenly there's a value that is not defined for the hyperbola. So it literally is a hole in the graph like this. But the pixels on our calculator screen are not detailed enough that it will not show you this hole. We have to look for it and find it. Sorry, but our calculators are going to let us down a little bit on this point. So fortunately, we can get both vertical and horizontal asymptotes out of the equation when it's given to us in this form. So this is really nice. In the next section, it won't be given to us in this format, so let's just enjoy this type when they make it easy for us. The denominator, wherever this denominator is 0, is a vertical asymptote. So you just, like what it says here in the parentheses, set x minus h equals 0 and solve it. So that could be like if the denominator is x minus 7, set that equal to 0, and you have a vertical asymptote at x equals 7. And this number k just gives you the horizontal asymptote. If that says a -4, then y equals -4 is the horizontal asymptote. So this is actually pretty easy. And that is all you need for section 9.6. Thanks. All right, another mistake. This is what you need for section 9.5. I'm going to go broke buying Starburst for you guys. All right, thanks.